This is Boyles and Charles's law problems and problems with gas laws. So the first gas law to look at is one where pressure and volume vary. We're going to keep the amount of gas in the container constant, and also we're going to keep the temperature constant, which is the speed. So right now I've got this container set to as small of a volume as it could possibly be. I know volume is three-dimensional, and this is a two-dimensional sort of box, but think of it as you can see through it and it's really in three dimensions. So anyway, get a rough idea looking at it what the size of the amount of the collisions are right now. And now I'm going to increase the volume and look at what the pressure does. By the way, the pressure right now is at about 61 atmospheres. If I make the volume much bigger, hopefully you can see that the collisions definitely went down less. And when I say the collisions, I mean the collisions with the walls of the container, not with the particles with each other. And see, the pressure did drop down to 22. So as volume goes up, pressure goes down. The opposite thing will happen. I'll make the volume much smaller again. They have more collisions with the walls of the container. And therefore, then the pressure increases. So what you're seeing so far is that pressure goes up, volume goes down. When pressure goes down, volume goes up. And that's what we say is an inversely proportional relationship. And what other scientists have done then with this is they've actually put gas in a container and they've looked at some of these values and they started seeing this sort of relationship. So the container that you maybe have seen them might look something like this, where they have certain pressures and different volumes, and just, they'd vary one of them, maybe vary the volume, and then they'd measure the pressure, and these might be some examples of what they get. And if you are to multiply the pressure times the volume, so maybe I do something like this, I'm just going to see what sort of thing that I get. What does this end up equaling? So if I do 14 in the first case, and I times it by 61 for the volume that I end up getting when I measure that, I'm going to get 854. I can do that for the next one, which is 28 times 31, and I would also get 854. And if I do it for the last one, 84 times 11, I would also get 854. Now these numbers, getting 854 each time, is only in ideal cases. In real life, if a gas followed this law, you would get numbers maybe close to 854, and that's just for this particular gas that's in these syringes or these pistons that are sitting in the picture. If you were to switch the system up, you might get a different number than 854. But you're always going to find that when you change one of them and get the other one, you're always going to get this constant value. And so what this led to, the scientist Boyles studied this, and he found out that he got these sorts of relationships. See if I can't straighten that out for you. There we go. And what it really leads to is what you first saw right here. That pressure times volume is some sort of constant. And you can see we got a constant no matter what the pressure was or the volume for this particular system. We got 854. If we change the system, maybe we do a different starting pressure, different volume, we might get a different constant. But a gas that follows Boyle's law will always have that same number. The more useful form of this, though, however, is this form right here, this equation that you see, where pressure 1 times volume 1 equals pressure 2 times volume 2. That's going to allow us to solve a lot of math equations. The last thing about Boyle's law and pressure and volume, going back to the fact that they vary inversely proportionally, if you were to graph them, this is the graph that you would end up seeing. That's the typical inversely proportional graph. Now that current graph has volume on the y-axis and pressure on the x-axis, but the reality is it doesn't matter. You could flip those and you'd get the same looking graph. So any gas that follows Boyle's law, when you keep the temperature and the amount of moles constant, you can always do this relationship, and they will create that graph that you see on the slide. So this would be the first problem that you would use that Boyle's law equation, P1V1 equals P2V2 for. and it would work pretty well for this. But I think what I'm going to do is I'm going to let you try this one on your own. And you might think, well, wait a minute, why would I do that? Why don't you go through it? Well, I'll let you go through it and figure it out. I'm going to go to the next one, actually, which is a harder question. And so if you can understand what I did on the second one, you should be able to go back and get this one. Okay, so here I'm going to read this question. And the first number I see without reading any more is 300 milliliters. I know that's a volume, so right away I'm writing down volume 1 equals 300 milliliters. I keep reading, and the next number I see is 800 millimeters of mercury. So that tells me right away, hey, that millimeters of mercury is a pressure. Put in P1. P1 equals millimeters of mercury. So I will then add that in. 800 mmHg. Keep reading. You see a question word, what? And then we are going to also see new volume. So I'm going to actually write that in because it tells me I'm looking for the volume. And I want to just maybe keep track of that so I don't lose track of that kind of stuff. So I'll put V2 equals question mark. I keep reading and I see liters. I'm going to actually underline that here just because that is quite important to make sure that I might notice it's different units than my volume. And then when I keep reading, I see 2.5 atmospheres. Atmospheres is a pressure, so I'm actually going to write in here that P2 equals 2.5 atmospheres. All right, so I have some issues here with the units, and first one was milliliters and liters. And I'm going to convert the milliliters into liters. So right now I'm writing 300 milliliters, and I'm using just the fact that 1,000 milliliters per liter conversion, and I'm going to convert this. 300 divided by 1,000 is going to make it equal 0.3 liters. The other problem that I'm having is that my pressure units don't line up. And it doesn't really matter which one I convert to which. I could convert millimeters of mercury to atmospheres, but right now I'm just choosing to convert atmospheres to millimeters of mercury. Just as long as they match, that's all I have to do. So I'm doing my pressure conversions that we learned a couple days ago here, and 2.5 atmospheres, and I'm using the conversion that 1 atmosphere is 760 millimeters of mercury. So 2.5 times 760 gives me 1,900 millimeters of mercury. And I'm going to write my values in because those are the units and numbers that I really want to use. So here I'm transferring them in back to the original table. And same thing with my volume one. Now I have everything here that I want to use. And so now I'll write down the equation. This is Boyles' law for whenever I have pressures and volumes changing. And I'll just plug in the numbers and units that I now have over on the left there that I'm keeping track of. So my original pressure was 800. My original volume is 0.3. And my new pressure is 1,900 millimeters of mercury. What's the new volume? And I'm just going to get V2 all by itself. So I'm dividing both sides by 1,900. The opposite of times 1,900, which V2 is originally, is divide by it. You can see the units canceling there. So I'm left with liters, the unit that I want. And therefore I get the final answer here that V2 equals 0.1. I'm going to round a little bit, 0.13 liters. Notice that my volume went down. It went from 0.3 liters down to 0.13, and my pressure went up. Okay, remember that was the relationship that we saw before, that when pressure goes up, volume goes down, and vice versa. And I'm assuming in this question that I'm keeping moles of gas constant and temperature constant. The question doesn't say anything about those things, so I have to make that assumption. If I don't, I can't solve the problem. Okay, so the next relationship looks at keeping pressure constant and amount of gas constant. And I'm going to change the temperature, and we'll see what happens to the volume. This one sometimes visually can be a little bit harder to see. So remember, temperature is how fast the particles are moving. Pressure is the number of collisions with the container that the particles have, and volume would be the size of the container. So right now, you can kind of get a rough visualization of how many collisions with the walls of the container I have. I'm about to increase the temperature and think that's going to make these particles move faster. It's going to increase the number of collisions. But for this relationship, I'm trying to say I want to keep the collisions the same. So if I'm going to increase the speed or the temperature of these particles, the volume is going to have to increase to keep the number of collisions the same. Otherwise, if it didn't increase, I'd get a lot more collisions, more pressure, and that would mean pressure would not be constant. So notice as I increase the temperature, the volume of this box got bigger. If I lower the temperature and cool it down, well, now I'm slowing the particles down. And in order to keep the collisions or the pressure the same, I need to make the volume smaller. So whatever I do to the temperature, the volume does exactly the same thing. When one goes up, so does the other one. When temperature goes down, so does volume. Looking at the volume and temperature relationship, as volume goes up, that must mean the temperature of the gas went up, and as the volume of the gas went down, the temperature must have also went down. Now this only holds true if we're keeping the pressure of the gas and the amount of gas constant. If we're letting all those things change as well, the pressure and the amount of gas, well then when the volume goes up, maybe the temperature will go up or something, right? We can't look at only two variables if we've got like four of them changing at once, sort of, so to speak. Okay, so these are proportional because when one goes up, the other goes up, or when one goes down, the other goes down. And so the math equation that leads to that, the proportional math equation, looks like this right here. V1 over T1 equals V2 over T2. If you were to graph this, you would see a graph that would look like this. There's the typical proportional graph. Typically, temperature is listed on the x-axis. Notice, though, this is pretty important. Notice that the x-axis has a temperature in Kelvin. That's very important. When doing any equation or any mathematics with any of these gas laws, you have to remember to have your temperatures always be in Kelvin. Kelvin is the absolute scale. Remember, temperature is a measurement of how fast the particles move. And you can't get any slower than not moving. So that would be 0 Kelvin. It doesn't make sense to have a negative temperature or a negative speed in a sense unless you're dealing with direction, and we're not dealing with direction with these gases. Now, it turns out volume is actually also an absolute scale. This is why temperature must be in the absolute scale, because volume is also in the absolute scale. Volume is how much space the particles take up. It doesn't make sense to say that these particles take up -5 liters. We wouldn't say something like that because there's no direction on the volume. Actually, pressure is an absolute scale too. Pressure is measuring the collisions that the particles have with the walls of the container, and it also wouldn't make sense to say, well, there are -8 collisions with this container. So we do need to make sure that we're using the absolute scale, which is the Kelvin scale. Okay, one other thing that I wanted to put in here was that when some of the first measurements of the absolute zero were determined, this is what they did. I'll move this thing up here so that we can see it. They went and they plotted this. They plotted the graphs here, just some points that they maybe would have been able to actually experimentally measure, would have likely have been up in this region, maybe up in here. And then what they thought they would do is that they would extend their line and to see what would it be, what would the temperature be if there was 0 volume and they get into this region here. And this is how the first estimates of absolute zero were done. Now it turns out some goofy stuff kind of happens with the attractions of the particles when you get close to absolute zero. So they were a little bit off doing it with this method, but it actually gave a fairly decent approximation. All right, let's take a look at this one. 300 milliliters of a gas. So right away, I know the volume is 300 milliliters, so I'm going to write that down before I read any further. Let's see, I keep reading here, originally at 30 degrees. Okay, I'll write down, that's a temperature. T1 equals 30 degrees. Keep reading here. What would the new volume be? So I see a question word there. Looks like I'm looking for volume, so I'm going to write down V2 equals question mark. And then I keep reading. I see something, temperature is raised to 60 degrees. So I'm going to write that out. T2 here equals 60 degrees. Now I got all my stuff written down. I don't ever have to read the question again. Everything's set. First thing I'm doing here is converting these temperatures to kelvins, right? Remember, volume and pressure are absolute scales, meaning the lowest pressure that I can get is 0. The lowest possible volume I can get is 0. I need to use the temperature scale that also the lowest temperature is 0. So each temperature, I'm going to add 273.152 to get the Kelvin temperature. So that is what I will use. These are called absolute temperatures because Kelvin cannot go any lower than 0. All right. Now, the equation that I want to use. Oh, by the way, I want to highlight what I'm using here. So volume, keep in mind, I have it in milliliters now. So that means when I solve, I'm going to have a volume in milliliters as well for my answer. Okay, here's the equation that I want to use. V1 over T1 equals V2 over T2. I am now just going to rewrite that, filling in the stuff that I know, making sure to use the Kelvin temperatures. Whoops. There we go. Look more like 303.15 here. V2, don't know it. And lastly, my last Kelvin temperature. All right, so how do you solve something like this? Well, for a lot of us, the easiest way is to cross multiply. So I'm going to multiply this part here, 300 times 333.15. So I'll write that down here. And that has to equal these two things times each other. So V2 times 303.15. All right, so if I multiply the left side, I get 99,945 equals V2 times 303.15. I want to get V2 all by itself. Right now it's times 303.15, so I'm going to divide by 303.15 on both sides. I'm just checking my units as well. You can see that volume 2 is going to be in units of milliliters, so the last thing I'm going to do is 99,945 divided by 303.15, and I get a volume of about 330 milliliters with a little bit of rounding. Notice my temperature increased from 30 up to 60. Therefore, that must mean my volume should increase as well. Volume and temperature are proportional. So here is another Charles' Law problem, and I think I'm going to let you try this one on your own. So pause now and try it, see what you get for an answer. And when you unpause, I'll be back and tell you the answer. Pause now. Are you ready? Okay, here we go. Here's the answer. The answer is approximately 420 degrees Celsius. Remember to have converted this one originally in Kelvin, and then you have to change it back to Celsius when you're all done. So, in order to use Charles' law and Boyles' law, we are making two main assumptions. Those two equations, no matter what you think of them, are relatively simple as to what they would look like if we didn't make these assumptions. So, those two assumptions assume what is called an ideal gas. And the two main things, one of them is this. Now, this is not really true, but we are making this assumption to make the math easy for us. And the first assumption is that any of the particles in these systems don't have any attractive forces. If you can remember way back when, those were things like hydrogen bonding or London dispersion forces or dipole-dipole forces. So is this a really good assumption? Well, it depends. If you're talking about things like helium or nitrogen or oxygen, things that are pretty small particles, small gases, don't have really high London dispersion forces, definitely no hydrogen bonding, no dipole-dipole, then yeah, this is a good assumption. So what we find is, you could go through and always calculate these values. But if you were to take steam, so gaseous water, water has hydrogen bonding and dipole-dipole forces. So no matter what number we calculate out of all these math equations that we've used so far, that number we calculate probably is going to be farther away from the actual experimental value that we measure. But if we did that with something like nitrogen gas, which doesn't have those forces and stuff, this is a good assumption, and therefore the math is pretty good approximation. The other assumption that we are making is this one, and that we are thinking that the volume of these gas particles don't take up space. Now, in reality, do gas particles take up space? Absolutely. But we are making the assumption that they don't. And that makes the math easier for us. Once we get through this whole thing, at the very end, we'll show you at least one of these approximations that has a little extra math involved that tries to take into account what real gases look like. So we are using ideal gases, which don't exist, but we're using them because they're easy for us to describe and work with, and we're trying to use them to describe how real gases are behaving. Sometimes it's great, and sometimes it's not. So again, why do we make these assumptions? Well, the gas laws, V1 over T1 equals V2 over T2, and P1 V1 equals P2 V2, including other gas laws that we will get to later on other days. These laws, when we solve for a pressure or a temperature or a volume, are actually often a very good answer to what will actually happen. So they're very useful in engineering and design applications. And it also makes the math much easier. We will eventually get to, like I said before, one of them where the math is a little bit trickier. It's not too tricky, but if you were to see some of these things that we aren't going to use, they have a lot of intensive math involved. And so we can get some pretty good approximations just by using this more simple, relatively simple math.